Okay, as you study more and more math, you're going to start to recognize certain integration problems. One is this one over here, minus infinity to infinity, 1 over the root of 2 pi, e to the minus x squared over 2 dx, and that equals 1, right? Let me show you where this is written in notes, by the way. Actually, that one's not written in the notes, so I'll talk about it then. We'll get to ones written in the notes, by the way. This is a standard normal curve. And the normal curve looks like this over here. And it's an even function, looks like this over here. And this is the y-axis, by the way, and this is x. It's an even function, all right? In other words, this is equal to that over there. So then what I'd write down is, well, if that's true, then 0 to infinity, 1 over the root of 2 pi, e to the minus x squared over 2 dx would equal 1/2, all right? Let me show you where that's written. I thought the other one's going to be written, but it's not. So I'm going to say this one's written down over here. 0 to infinity, 1 over the root of 2 pi, e to the minus x squared over 2. It's a really famous integration problem. And it also can be verified, right? But anyway, let's not worry about that. Let's just say that I knew this, right? That if I know that, it's a good idea to know what you know. And it's a standard normal. Very famous. If you took an introductory course in statistics, that should be sort of like ingrained in your mind. You had tables for it to look it up, but a calculator can do these integrations pretty readily now. At least they can approximate them. So what I want to do is look at this integration and say, it sure does look like this one here, but the bottom line, it's really not the same one. So what I want to do is I want to, maybe make it look like it. And I'll tell you what we're working on. We're working on this guy over here, and I really want it to look like this one over here. So I'm going to start to write a little bit differently. I'm going to put this over here as 0 to infinity. I'm going to pull out this, 1 over the root 2 pi. And then I'm going to say e, and I'm going to put down minus, I'm going to use the letter u now. So I'm going to say u squared over 2, and then du. And I know that's equal to 1/2. I know that much. Right, so what I'm going to do now is I'm going to multiply both sides by the square root of 2 pi. And what do you get? You get 0 to infinity, and then I'm going to put down e to the minus u squared over 2 du would be the root of 2 pi over 2. I can write that a little differently. I can write it as pi over the root of pi over 2. All right? Now what I want to do is I want to make a substitution now. And someone says, what substitution are you going to make? I got to look at it. So I really want this thing to look like this over here. So I'm going to look at that and try to get it to look sort of like that. So I see the minus sign. And then I'm going to say u over root 2 squared. Well, that certainly would give me what I want. All right, so this is what I want to do. So let me point out what I want to do. I'm going to make a substitution. I'm going to say, again, I'm looking at the integration. I'm going to make a substitution now. I'm going to say u over root 2 is equal to x. And then I'm going to say du, that's going to be 1 over root 2 now, would equal dx. And I think I'm ready to pop this in now. All right? So let's do it. Now, if u is 0, x would be 0. All right? Now, if u is infinity, x would be infinity. Then when you get e, and I got to do something tricky over here. I got to square this, so it's going to be minus. And if I square that, I would get u squared over 2 equals x squared. So this is going to be just simply x squared now. All right? And then what's the dx equal to? It's really 1 over root 2 du. And what's that equal to? Well, it's equal to, let's see, I'm going to write it a little differently now, root pi over root 2. I'm going to multiply both sides by root 2, and what do you get? 0 to infinity, e to the minus x squared, d, you know what, I made a mistake in copy. Let me just make sure I said something Um, you know what? I got to back up. I really did make a mistake here, and this is not true. And I'm glad I looked. I really am glad I looked. Let's write this down again. 0 to infinity, e to the minus x squared, and du is going to be root 2 dx. Sorry about that. All right, let me make sure I said that right. Yeah, du is root 2 dx. And what does this equal? It equals root pi over root 2. All right, that comes from up here. What I'm going to do now, divide both sides by root 2. And what do you get? You get 0 to infinity, e to the minus x squared, dx equals root pi. And if I'm dividing by root 2, it's like root 2 times root 2, which is 2. This is my answer. All right? So let's just look at the key and make sure the key is at least giving us the answer over here. And this isn't often a problem students have. They're trying to aim for an answer. If they don't get the answer, they fudge around until they get the right answer. But the bottom line is we used a well-known definite integral, all right? So we used a well-known definite integral. So what was well-known definite integral? It's standard normal, very well known. It's one that you probably should know about. Now, again, I'm not going to say you remember that, but if you take enough statistics, you'll remember that, all right? So I want to point out another way of doing the problem, and it's kind of an introduction to the concept of a Jacobian. And, I would pay attention to this over here, what's happening over here, what I'm doing over here, all right? So, it gets a little bit complicated, but the bottom line is, I'm writing them down twice, I and I. They're both the same integral. I'm just using different letters, multiplying it together. I get what's known as a double integral right now. And later in the course, not saying later course, but later in this worksheet, we're going to see a lot of these double integrals. And where's that double integral come from? Well, if you do I times I, right, what are you going to get? E to the minus x squared times e to the minus y squared. We'll just sum the exponents together. It's going to be minus x squared minus y squared. And you do get a dx dy or a dy dx, depending on what order you're putting it in. And then over here, move to polar coordinates. Yeah, not a bad idea. Right? Maybe it's going to work out. Maybe not. All right? And then, moving into, and again, polar coordinates are introduced to you when you took pre-calculus. So, x equals this, y equals that, x squared plus y squared equals r squared. Keep following along. Again, introduction to Jacobian. We'll talk about this more. It's part of, I'm going to say not traditionally a part of Calc 2, except at some schools. It's typically when you start getting into multivariate calculus in Calc 3, but sometimes it's done in Calc 2. I would not worry about this. We'll talk about it in more detail, but they're starting to talk about partial derivatives, all right? And again, we'll go through these things, all right? So this is the Jacobian. So, the partial of x with respect to r, partial of y with respect to theta. So I'm differentiating these guys up here, all right? That's what I'm doing. Right? You can look at that if you like. And it kind of simplifies nicely. It really simplifies nicely. And would simplify, really, really nicely. This thing over here. That's amazing, all right? So I just pop it in. And this first one with respect to r, it's a fairly easy integration to do. And this is a fairly integration. And I'm just backing out of it one step at a time. And you get this over here, and that's I squared. Then when you do take the square root of both sides, principal root, by the way, root pi over 2. Now, granted, I don't think this is the most obvious path to take at this point, but it's one you should start to look at. To me, if I were doing the problem, I wouldn't be doing that. But I'm looking at it. What am I doing over here? Going back to this thing. We did the standard normal, which is the most attractive thing you could possibly do for a problem like this because it looks just like it. Again, if you have a known integral with known result, you probably want to reuse that over and over again. But we're getting it. What are we getting? We're getting the correct answer. When I use this thing over here, which we'll talk about in more detail later, you'll get that answer too. What answer are we talking about? The one we said right over here. We'll get this. All right? Thank you.